Yep. Again, thanks to the organizers. This is my second FRAC meet. So, yeah, what really impresses me about this meeting is that it's really wide spectrum, right? You get to hear talks from different interdisciplinary areas. So, I'm going to talk about a few things. I mean, which the title is non-spherical particle at an interfaces and their mechanical response. So, this is a work that I am going to present like 10 years of work, okay, starting with some very recent work that has been done with a lot of students in IIT Madras in collaboration with Sumesh, who was at IITM Chemical Engineering as well. And I am going to go back in time and talk a little bit about the work that I did as a part of my PhD thesis. So, so you can stop me at any point, if you have any issues. So, okay. So, there's a lot of work looking at particles in the bulk, okay, wherein you have particles dispersed in a fluid. You can work with nanoparticle dispersions or colloidal dispersions. There's a lot of interest looking at their self-assembly, their rheological behavior, stuff like that. And the talk that I'm going to talk today, we're going to talk about an interface either between water, oil or water, air, or any immersible fluids. You put the colloidal particles at the interface. So, the field is something called as particles at interfaces, or people also call it as particle laden interfaces. Okay, that's going to be the focus of today's talk. So, but more specifically, I'm going to look at cases where what is sitting at the interface is a non-spherical particle. Okay, so we're going to look at may not be all the cases, but we have this. Chemists have really worked out nice recipes for making particles. So, we just follow these recipes and then we make particles of all different kinds. So, this scale bar is about 1 micrometer in length. So, we are basically working with colloidal particles which have a size range of the order of a micrometer or less. Okay, that's now, when you look at particles in the bulk versus interfaces, so all of us know that whenever you have a charged particles in the bulk, okay, that's the central spherical looking part is a spherical particle which is positively charged. The moment you disperse such particles in a fluid, you are going to have these counter ions which are going to come into picture, and there is a nice formation of what is called the electrical double layer. Okay, and this electrical double layer concept is known, and people talk about electrical double layer interactions, the repulsive forces between the particles in the solution. Now, what happens when you put a particle at the interface? This is in the bulk. The moment you put this particle at the interface, because only a part of the particle is in contact with water, dissociation happens only on one side. Okay, and so therefore, you can basically think about this like a dipole, right? Because there's a in this case a negatively charged particle, which forms, right, and then corresponding there are positively charged ions in solution. So, that kind of forms a dipole, and there is a dipole repulsion, okay, compared to the electrical double layer repulsion in the bulk. In this case, you are going to have a dipolar interactions, and people have kind of shown that such dipolar repulsion can really lead to structures at the interface where the interparticle spacing. So, this is a case of a 3 micrometer particle. If you look at the interparticle spacing is of the order of 10 micrometer or more. So, such long range repulsion, okay, that comes because of the positioning of charged particle interface is that originates from the dipolar repulsion between the particle that you have at the interface. Okay. So, that means what I am trying to say, certain type of interactions are modified when you put the particles at interface. Okay, that is the case of electrostatic interactions or electrical double layer interactions, but certain new types of interactions can also arise. Okay, for example, this is a case of if you think about this flat line as an interface, I have a weightless particle sitting at the interface. The moment I make the particle larger, okay, larger and larger, at some point you are going to have a interface deformation. Okay, and this interface deformation mediated interactions are what are called as capillary interactions, and these again help in some kind of assembly of these particles at the interface. Okay, so now, having told you that the interactions can be either modified or new interactions can arise when you talk about particle interfaces, I am going to talk about some unusual behavior of particle laden interfaces. I am going to give two examples. One is in a case of a drying drop problem, okay, which we have been working for a few years now. And all of us know that if you have a flat surface and if you put in a drop and if this drop contains particles, okay, this is what is called as a sessile drop configuration, that is a drop sitting on a surface, and if the liquid that is a part of this drop, if it evaporates, and it leads to something called as a coffee ring formation, where all the particles that you had in the bulk, they go and deposit at the edge. Okay, that is what is called as a classic coffee ring problem. Now, what we were trying to do was do similar experiments, but with particles that look like a rice particle or a needle like particle. So, these are ellipsoids. The major axis of these ellipsoids is about 250 nanometers and the minor axis is about 50 nanometers, aspect ratio close to 5. Okay. All we have is basically a substrate and you have a droplet, and droplet contain these particles, okay, and we are just drying, right. It's on a solid surface. It's on a solid surface. Now, so we kind of got interested into this problem looking at what does the orientation do, like I have a particle which is sitting like this is what is called a sessile drop configuration, particle which is kind of inverted, what is called as a pendant drop configuration, this is a vertical configuration, and these are some results from these experiments. So, this is so we have basically taken substrates of different wettability, contact angle of 12, that is a nicely spreading surface, contact angle 30 and contact angle 90. You can clearly see that for the sessile drop case, that is the droplet sitting on a surface, you always get a coffee ring formation where the edge has all the particles that were there in the this. Yeah.
So, how do you stabilize these two structures?
This and this. If you take small enough drop, that's good enough. So, for example, if I go to this configuration, what you do is you take a surface, okay, and then what you do is you take a micropipette and then put a fluid of certain volume. But now, if the fluid volume becomes too much, like say maybe 50 microliter drop or 100 microliter drop, it basically detaches. But for smaller droplets, surface tension is good enough to hold these things to the surface. Yeah. As I said, right, I mean, yeah, if it's too big, it detaches, but we have done experiments all the way up to 10-20 microliters. It's fairly it works. Density of, yeah, of course, right, because of course it's a balance between surface tension forces and gravity, right. Of course, if you use denser fluids and larger volumes, of course the gravity is going to enable it to detach from the surface. Yeah. Yeah.
This vertical case,
yeah.
The shape of the droplet must be different so it deforms?
It is actually, because if you look at this the center image, you can see it's elongated, right.
But not only that, also it will not be symmetric.
Oh, I completely agree with you. Yes, yeah. So, I mean, so the way we understand all these deposit formation, is that we kind of see that whenever you are drying droplets in these configurations, there's something called the adsorption of particles to the drop surface, and then once the particles go to the interface, there's a migration of particles, okay, and this migration of particles is along the interface, and that is what is leading to such I'm going to show you a more convincing convincing argument that adsorption of the particles to the drop surface does occur. So, these are couple of different configurations, sessile droplets and pendant drop. This T is the time instant at which these images have been acquired, and TF is what is called a total evaporation time. Okay. So, that as a function of time, we are basically looking at the drop surface for the sessile case and the pendant drop case, and you can clearly see that at some point, okay, at T by TF close to 0.5, the nice hemispherical shape is gone, okay, and there is some kind of a distortion of the droplet surface. And also if you look at the pendant drop case, you see these wrinkling behavior, okay. This is an indication of the fact that interface is doing something funny, okay, and then there are some arguments in the literature as to when you have a drying droplet, this interface, okay, that's a drop surface basically descends, right, and the descending of the drop interface is basically what is leading to the capture of particles to the interface, okay. So, just to the take home message from this thing, there's a drop deformation and there's a formation of some wrinkles and buckling, and this kind of indicates the elastic nature of the particle laden interface, okay, that's the take home here. I just have a video just to show you that okay, let's see that. Oh, just I mean, whatever I showed in the picture. So I'm going to show it in the form of a video. This is as I said, it's a pendant drop. That is a drop hanging on a surface, and it is being evaporated under ambient conditions. Typically, we work with about 2 microliter drops, and as you will see that as the drying proceeds, at some point you start seeing these wrinkle formations, right? Okay, and then ultimately this whatever wrinkled surface, it kind of goes and deposits onto the substrate that we are basically using for these experiments. Okay, so I'm going to give examples from some other kind of experiments where we were looking at what is called as a drop compression experiments. Okay, again these experiments are fairly simple. What you can think about is that you can think about a balloon. Okay, and what I have done is I have filled this balloon with a dispersion of these particles. Okay, so that's the balloon. Okay, so this is actually what is called a pendant drop. Okay, that's you have a syringe. Okay, and then you have made a small drop and by injecting a fluid from the syringe. Okay, and if you are working with about 10-20 microliter droplets, it basically shakes takes this shape that is again governed by the balance between the surface tension and gravity. Okay, and you should imagine that this balloon or this droplet actually has particles, and these exactly same particle that we used in the previous experiment, and either I can put this in air or I can immerse it in oil. So then I basically create a oil water interface or a air water interface. Okay, that's the. Now I'm going to again show you 2 movies. What is inside the drop is exactly the same. These are ellipsoidal particles dispersed in the fluid. The only thing that is different is the pH of the solution that you have inside. Okay, one case the pH is 2, other case the pH is 6.5. Okay, and what I'm going to show you is a movie where this drop has been suspending in the fluid for about 2 hours, and after 2 hours we have tried to withdraw the fluid. Okay, this is these droplets have been immersed in oil. So no, it doesn't. Okay, only thing is if you put it in air, there's going to be evaporation that I have to worry about, but if you put it in oil, that evaporation is minimized, so it helps you in doing cleaner experiment. That's the only difference. Yeah. Okay, and so what I can do when I withdraw the fluid is basically I'm changing the volume, right, of the fluid, and then because I'm changing the volume, I am also changing the interfacial area. Okay, so if there is something at the interface, when I'm withdrawing, I'm basically reducing the area that is available for the particle. Okay, now let me show you the movie. So one is a case where so left is a case where the pH was 2 and I am withdrawing the fluid. Okay, there's an isotropic shrinkage, and at some point all the fluid goes into the syringe. Okay, whereas if you take the case where the pH is 6.5, when I'm trying to withdraw the fluid, I see this nice wrinkling behavior. Okay, again this points to the similar kind of argument that we believe that the particles go to the interface as I compress it. Okay, and then that's what is leading to these behavior. So now you can ask the question is what is different at these 2 pH. So same particles, if you look at their charge, okay, it turns out that at pH 2, okay, where I saw just a isotropic shrinkage, the particles are highly charged. The zeta potential, even in reasonably high salt concentration, the zeta potential is fairly high, plus 40 millivolts, indicating that the particles are highly charged. But if I go to 6.5, which is somewhere here, the particles are weakly charged. Okay, so these 2 contrasting behavior that you saw. Okay, in one case where there was an isotropic kind of a compression, in the other case the formation of this wrinkling, we kind of think that is kind of associated with the charge of the particle. This is exactly the same same video, but I've taken different frames. This V by V naught kind of tells you something of the compression ratio, right? I begin with V by V naught 1. As I withdraw the fluid, I'm basically decreasing this V by V naught. Okay, and the case pH 2.0 where the particles are highly charged, okay, there's as I said isotropic shrinkage, but however if you go to the case where the particles are weakly charged, we see this nice wrinkling behavior. Okay, you can do some quantitative measurements of a few things. What we have done is we have looked at how the surface tension okay, changes as a function of time. For different cases, one is water decane. This is a water droplet without any particles in contact with decane, and that's your black squares. Now, as expected, the interfacial tension should not change, right, because this is what I have done is I have put a droplet. I am basically measuring surface tension as a function of time. Okay, so this basically interfacial tension remains constant. That means there is a pure interface. There is nothing that is surface active. However, if I change the fluid, I replace water with hematite particle dispersion at pH 2, where the particles are highly charged. Again, I see a very similar behavior. Okay, that is your red circles. Again, interfacial tension remains more or less flat. Okay, again, just to say that the particles, though there are particles, because of the fact that they are highly charged, they are still not surface active. Okay. However, I change the pH to 2 and 6.5, exactly same particle, we see a drop in the surface tension, and the drop in the surface tension is typically associated with the adsorption of surface active species to the interface. Okay. And what is interesting to note is that there seems to be kind of two slopes here. This is a case where there is a larger a steep decrease in the surface tension, followed by a kind of a more gradual decrease, and we think that is because of the fact that in the initial stages the interface is free. All the particles which approach the interface can easily adsorb to the interface, but once the interface is populated with particles, there is an additional resistance, okay, because of which there is a change in the slope.
What is the meaning of high pH?
So okay, let me go back and then explain you based on this. Okay, what I mean by the so in this case we had used this hematite particle, and these hematite particles actually I can tune the surface charge on the surface by changing the pH. Okay, and that's the pH all the way from acidic pH, okay, to basic pH. Okay, depending upon whether I am at close to isoelectric point where the particles are uncharged. Okay, acidically acidic pH the particles are positively charged, and basic pH the particles are negatively charged. So therefore, this hematite particle system is a very nice system to really tune the surface charge on the particle without adding any other additives other than just manipulating the pH. Yeah. Okay. So now, so that's again just to make the point that if the particles are highly charged, the interfacial tension remains constant, indicating that particles are not surface active. But if the case where the particles are weakly charged, there is a drop in the surface tension, which is an indication of the adsorption of particle interface. You have a question?
The pH you are essentially changing the range of interaction between the particles, the repulsion.
Yes, yes.
So if you change the particle concentration, you have a similar effect.
So typically we see because whenever people work with interface experiments, you typically work with a very dilute concentration. In this case 0.38% by volume, that's too little. Okay, I mean things like what you're trying to mention. Okay, I think it would become important if you have sufficiently larger concentration of particles. But in this case, the number of particles in the droplet is something like 10 per 12 per milliliter. Okay, which is significantly low for you to think about the particle-particle interactions. Oh, you're talking about at the surface.
Yeah, at the surface.
Yeah, at the surface, yes. I mean, see, if you play around with this particle concentration, if I were to do it at a little lower or a little higher, we kind of see a similar kind of course, these slopes could be different because because of the fact that you have more number of particles, maybe the adsorption may happen a little quicker than at higher concentration, because there's a more probability of them finding the interface. But at least the overall behavior would be very similar. So now it turns out that this wrinkling and buckling that we see in the case where the particles are adsorbed to the interface is kind of very reversible. I can start with this, I can withdraw the fluid, I can go back to this buckled state, and then I put the fluid back. It's a very nice reversible transition. So we have done this multiple cycles, it seems to be doing. Yeah.
Sorry.
Yeah, go ahead. Yeah, please. Yeah.
So this observation, so why do you use this particle in the spherical particle? Just because you can tune the pH, or there is something special in this?
There's something special which I'm going to talk in the rest of the talk.
Okay.
Yeah. Now, okay, so what we have done is we have kind of some nice ways by which you can actually image this film. Okay, what we have done is if you, while keeping these things in a compressed state, if I basically chop off this film basically floats to the water surface. You know, I can actually take it out and I can do imaging. Okay, these lines that you see here, these lines, these are the wrinkles that you saw on the surface. Okay, and then the wrinkled surface, you know, if you look at microscopy, you know, it looks something like this. Okay, and what is interesting is that, you know, it's a single particle film. Okay, it's a film which is a single particle thick. Okay, and that's all that is required for you to see this very unusual behavior that you saw. Okay, so now just to wind up this part, okay, whether the buckling leads to, you know, isotropic shrinkage or this seems to depend on the charge. However, charge is not the only role, okay, because, you know, we have done similar exactly identical experiments with spherical particles, wherein we have kind of tuned the surface charge by adding, you know, salt. Okay, we see a similar, you know, surface tension versus time behavior, that is, you know, in the pure salt, in the pure fluid case, you know, the surface tension more or less remains constant. That's now on a log scale. Okay, and then if I go on adding more and more salt, I am reducing the repulsion. There is a larger drop in the surface tension. That means more and more particles go to the interface if you basically reduce the surface charge. However, we never see this wrinkling behavior in the case of spherical particles. Okay, so we have again done both drying drop experiments and drop compression experiments with, you know, fluids containing spherical particles. We never observe this unusual behavior, which kind of points to the fact that, you know, there seems to be some kind of a particle shape effect. Okay, so that's what I'm going to talk in the rest of the talk. Any more questions? Any questions? Okay. Okay, so now, so self-assembly of particles interface again is very widely studied. If you have spherical particles, I showed this picture, you know, right, there's a, you know, kind of more or less crystalline arrangement, very long gap between the particles, you know, there's a hexagonal order. If I look at this, you know, every particle has 6 neighbors. Okay, that's known. Now, all I have done here is exactly identical particles, and the particle shape has been changed. The moment you do that, you start seeing, you know, such a kind of a microstructure. What is interesting about this microstructure is, you know, if you look at all these aggregates, they're all like linear chains. Okay, all these aggregates are linear chains, and where, you know, the attachment between the particles occurs tip to tip. Okay, that's one, you know, observation. Of course, you do have some local regions, you know, where there's some kind of, you know, arrangements like this, but there are very few in number. Okay, we'll talk in the rest of the talk. Yeah. So these are experiments where what is being done going from B, C, D is, you know, you basically have increased the concentration of particles on the surface. Okay, and what you can clearly see is that, you know, the number of particles in the chain grow, right. If you look at compared to this and this, on an average there are more particles in the chain, and if there are enough in number, you kind of get a very nice percolating structure at the interface. Okay. This is I am basically changing density here. B, C, D. There's some surface coverage here, a little bit higher, a little bit higher. Yeah, and this typically happens at about 12-13%. That means you're able to get a percolating network at a much lower concentration than what you can see with spherical particles. Now, so it turns out that the reason why you have such aggregate formation in spite of the fact that the particles are charged, it is because of what is called as a interface deformation mediated interactions. That means if I put an ellipsoidal particle at the interface, okay, this is a surface evolver simulation where they have kind of captured how the interface deformation occurs around a particle. There is a region where there is a kind of a pulling of the interface, you know, in the vertical direction, and there is a depression where the interface basically goes down. Okay, and this is you know, kind of what is called as a quadrupolar interface deformation that happens if you put an elongated particle at the interface. Okay, and that's you know, data from a paper from you know, UPenn group, and these are our experiments where we have kind of held a particle at the interface, and we are looking at the interface deformation, and you can clearly see that bulging here, which is kind of seen in these simulations, and there is a depression that you see at the tip. Okay, you are basically looking at the ellipsoid in this direction. Okay, and this interface deformation, what it basically does is, you know, it leads to, so the moment even when the particles are several micrometer apart, this interface deformation is so strong that, you know, the two particles are basically pulled to each other, and the interface assembly occurs such that, you know, either there is a, so this is kind of a people talk about this in terms of what is called the capillary charge effects, in which case there is a like charge attraction. That means if you have a particle which is approaching another particle, the tip is going to be connected because, you know, the charges on at the tip is actually identical, right. So therefore, so in ellipsoidal particles, the only kind of assembly that you will see is either tip, okay, or the side. In this case, we have cases where, in this case, because of the fact that the particles are charged, okay, we are mostly seeing this, you know, tip, but we have also done experiments where the particles are a little bit weakly charged than what we have used here. In such cases, we mostly see the side arrangement, okay. So in this case, the assembly is kind of governed by these shape induced interface deformations that leads to these, you know, nice and interesting structures. Okay. Rajesh, you have a question? So this was okay. No, we have kind of, I haven't showed you the images of the cases where we have kind of worked with uncharged particles. If you work with uncharged particles, you will see a lot of cases where, you know, side is more dominant. Okay. So yeah. Now, so we have kind of in the recent years we have looked at particles of different shapes. So if you look at particles here, when you deposit ellipsoids at the interface, you will see that, you know, all these ellipsoids, they lie flat. Okay, that is, you know, they're you know, the major axis is kind of, you know, the parallel to the interface. The moment you go to, you know, other shaped particles like cubic particles, we kind of see multiple orientations. Okay, these are again imaging of the particles at the interface done in a particular way. I can talk to you a little bit about if you are interested in the details. And, you know, what we see, you know, the cuboids put it in the interface, they kind of take multiple orientations. Okay, they have this face up orientation, edge up, you know, vertex up. Okay, that's the top view and this is a side view. Okay, so and depending upon the orientation, again the interface deformation around these particles are also going to be different. Okay, in the case of ellipsoids, mostly people have reported either you know, the quadrupolar deformation, but if you look at you know, these cube like particles, people have reported, you know, both either the quadrupolar deformation or hexapolar, octopolar, depending upon the orientation of the particle at the interface. Okay, and what it, in terms of the assembly, we kind of see much more richer assembly. For example, in the case of ellipsoids, as I said, it could either be tip or side, but in this case, you know, we could also have, you know, vertex to the side, okay, or side, tip, you know, all kinds of other assemblies are possible. That is again kind of dictated by the fact that, you know, there are kind of interface deformations, and depending upon, you know, what kind of orientation the particles are at the interface, you kind of get these either linear structures, you know, or these triangular lattices and stuff like that. Okay. Now that we've kind of looked at assembly of these particles, I just want to spend a little bit of time talking about what is called as a surface rheology. Okay, just like, you know, you can do bulk rheological measurements, you can put this stuff at the interface, and I can also subject them to shear and, you know, oscillation. Okay, and the way these experiments are done is you create an interface and you put your measuring geometry right at the interface, and people use different kinds of measuring geometries. You could have a needle which I can, you know, kind of drive magnetically, or I can have a what is called a denouement ring. Okay, and I can actually either do continuous shearing or I can do oscillations. Okay, and so what you are looking at is some kind of a modulus measured as a function of strain. All this is actually data from spherical particles at water oil interface. Okay, and if you look at these numbers, you know, these are of the order of 10 power minus 3 Newton per meter. Okay, these are all for spherical particles, and this plot is for the case where we have elliptical particles. Okay, and so whenever we talk about, you know, G prime and G double prime as a function of frequency, if, you know, these is frequency independent, you know, you can think about as a gel like interface. Okay, and look at the magnitude of these modulus. Okay, this is much larger compared to the case of spherical particles. Okay, so therefore the elliptical particles put in an interface kind of behave like a gel, okay, with a modulus which is much larger than the spherical particles. And these are some strain sweep data where again you see kind of a classic, you know, a kind of a yielding behavior where you have frequency strain independent behavior of this G prime and G double prime at lower strains, okay, and then at some point when you deform these interfaces enough, okay, large enough, okay, you kind of see some kind of yielding, okay. So and this is basically comparison of spheres versus ellipsoids for different surface coverages, and just to make a point that the typical modulus values are of the order of at least one or more order larger than the case of ellipsoidal particles, which basically arises because of the fact that at a similar concentration these ellipsoidal particles form this interconnected network, and this interconnected network kind of yields at a much higher modulus compared to the cases where you have spherical particles sitting at the interface. So I am going to move on to a different kind of experiments. Yeah. So as I was saying, right, if I look at for example about 40% coverage, right, if you look at here, okay, I would say that the modulus is about maybe 1.5 magnitudes higher, right, okay. So I think the point, I don't think the slope is important. The point that I wanted to make is that for a given coverage, the monolayer with ellipsoids definitely have a higher modulus compared to that of spheres, okay. That's the point that I want to make from this plot. So I just want to move on to a different type of experiment. These are actually compression experiments, but done in what is called a Langmuir trough. Okay, these are basically, it's a rectangular trough in which you can put the fluid, okay, and then you can sprinkle particles on the surface, and there are these barriers, this and this, and these barriers I can actually move by a stepper motor. Okay. By doing that, what you are basically doing is you are basically reducing the area that is available for the particles. I begin with putting certain number of particles at the surface, and I move the barriers, okay, and by moving the barriers I can change the area, okay. The area that I am changing is the area that is available for the particles at the surface, and you can, there are troughs where you have a small a glass window which I can actually use for doing either optical microscopy, or I can do some light scattering experiment as I am compressing, okay. That is basically the microscope, and that is the Langmuir trough, okay. These are the barriers that you see here, okay, and you can do some in situ measurements. Along with this Langmuir trough, there is actually a rectangular plate which is what is called the Wilhelmy plate, and this Wilhelmy plate is typically used for picking up the surface tension, okay. As I am compressing it, what's the surface tension of the interface containing particles is what you can measure while you compress the monolayer, okay. Just to give you a quick heads up, so typically from this compression of monolayers, people extract data which is surface pressure versus area per particle of the molecule, and the surface pressure is basically defined as surface tension of pure interface minus surface tension with particles or with anything that you have on the surface, okay. You can think about this as an analog of PV diagram, okay. In the case of 3 dimensions, you talk, yeah. So okay, let me just put it this way. So now okay, so that's your trough, okay, and you fill the trough with liquid, and then you put stuff at the surface, okay. In this schematic, what is shown is a surfactant molecule sitting at the interface, okay. I picked up from one of the sources, okay, and then what you are doing is by compressing it. So initially, if you say for 4 molecules, the entire area is available now, initially. Now, exactly, okay. As I said, this is an analog of PV diagram, but in 2 dimensions, okay. I am only talking about surface pressure versus area now. Yeah. I am going to look at ellipsoids. I just want to, so people, I just want to make a point that when people look at surface pressure area isotherms, okay, you see some variation of how the surface pressure changes as a function of compression, right. Now that is kind of associated with the different phase transitions, okay. At initially, when you have very few molecules, you can think about like a gas like state. If you compress them enough, you could have a liquid like state, and then you could have some kind of a liquid crystalline order and stuff like that, okay. So this is a classic experimental setup where people look at phase transitions in 2 dimensions, and if you have way of doing microscopy and other kind of tools, I can basically map out the PV diagram in 2 dimensions. That's the point, okay. So, this is the surface pressure as a function of trough area for a case where we had put in spherical particles at the interface, okay, and this initial region which we call it as A is a case where there is some kind of a gas like state, okay. You can think about these particles as hard spheres, okay, and then they are non interacting, okay. All that you are doing by compression is you are basically bringing them together. So, initially the structure at this in this region A looks something like this, okay. There could be some aggregates because the particles are not charged, okay. However, as you start reducing the area that is available, at some point you start seeing an increase in the surface pressure at this point IP1, okay, and that is a case where we can kind of imagine them, imagine the particles as forming some kind of a 2D network. Now, all the particles are in contact, okay, and then the moment you start compressing further, there is some kind of resistance that comes because of the fact that now the particles have to rearrange, okay, and that happens, okay, and at some particular point IP3 we should expect the formation of a kind of a close packed system, okay, because these are I can, by moving the barrier I can still lead to there is enough empty space available, the particle can rearrange, and at this particular point your monolayer should look something like this, okay. If you do microscopy along these lines, this is what we see, okay. That is at IP3, that is the inflection point here, okay. We really form a 2D crystal, okay. It's a CP arrangement in 2 dimension, and again as you see like every particle has 6 neighbors close packed, right. And now what you do, if you compress the monolayer beyond this point IP3, you see there is a kind of a further increase in the surface pressure, and if you look microscopy, we see some kind of a buckling of the interface, okay. That is you should think about it as a 2D sheet. Now, you have compressed further, you should see the formation of these crusts and troughs, okay. The fact that these regions appear white is because it has come out of the interface. Now, the monolayer is not planar anymore, okay. There is an out of plane deformation, and there are people who talk about the dependence of this lambda versus particle size and stuff like that, and we kind of saw an average wavelength of the order of about 70 micrometer in this case. Yeah. No, in this case, I mean, see, as I said, right, these are not purely hard sphere, these are uncharged particles, but of course at the interface you have these interface deformation mediated interactions, okay, which we think is kind of minimal in this case, but I do not think we can think about it as an analogous of a hard sphere in 3 dimensions. Oh, 2D problem, okay. Correct. So you are talking about if I were to have 2D hard spheres, they exhibit some phase behavior. You are saying you are.
It should get some defects.
Okay.
We're not happy, we will get some defects.
So when you say defect in terms of a case where there are no particles at the.
And also the transition is very sharp.
Oh, I mean IP3
to IP2.
Okay, so I mean I would not say it's a perfect I mean it's a crystal, I agree, but of course there are some defects. I mean if you look at there's some orientation differences, right? If you look at the yeah. No. Yeah.
So there is non-monolithic behavior at high area. So
yeah. Here?
No, on the other side. So to the higher values.
Here?
Yes.
Okay. Yeah.
So there you can see for very high number it goes up and then it shoots up. If you are coming from that side.
From this side? Okay. So so I mean this minima, I mean yeah. So this minima, I don't want to put a lot of weight to this minima because of the fact that when you do these experiments, okay, what you do is you put in a dispersion of particles and a little bit of an alcohol, okay, because alcohol actually acts as a spreading agent, okay. During the initial stages of compression, okay, alcohol is still evaporating, okay, and we know that the presence of a small amount of alcohol reduces surface tension, okay. I mean I would say that no, this is for sure, because what you do is we have done an experiment where you put in you take the no, I don't think so, because we have done these experiments. Let me explain the experiment. You take water surface, water in a container, you put a small amount of alcohol on the surface, you put a Wilhelmine trough and you start measuring the surface tension. Okay, you will see that the surface tension between water and air, which is 72 millinewtons per meter, it will start decreasing, and this decrease happens until certain time, as long as the
It's a hydrophobic collapse. So that's why we are saying that.
no, it's nothing to do with the hydrophobicity or hydrophilicity of the colloid. This is something to do with the evaporation of the alcohol that I have used for spreading, okay, and the loss of that, okay, is known to initially when you add alcohol the surface tension goes down, but as it evaporates the what is that?
It will minimize the area, so the surface area.
No, the interfacial area that is available for everything is fixed, no, because once you take a once you are doing experiments in a fixed container, the interfacial area is fixed, right? There is no change in the interfacial area. Correct.
So basically these drops will again, so it aggregates and so it will minimize the acids.
Yeah, I mean, of course, these alcohol molecules does go to the interface, okay, and that's what is leading to the surface tension decrease.
So, Basa, in
Yeah.
that last thing, so you are saying that it leaves the fluid or the fluid is going with it? Or
I guess the fluid also, I don't think it
because you say that it is detached.
I think the whole interface also buckles, yes. Yeah, I don't think it will detach from the interface and then buckle, no.
So in case of spheres,
Mhm.
the interaction is mediated by the interface.
Mhm.
Is it symmetric, I guess?
It is symmetric if you are thinking about, a perfectly homogeneous particle, but people talk about surface roughness, charge heterogeneity, all of this can also lead to some of the complications, but
Formation of a neck or like this is just your speculation, because with a symmetric interaction you don't expect.
which one?
Like in B, the image in B.
Image in B or here?
In B. So
This one?
Is something that you don't expect if you have a symmetric interaction.
Unless
Is
there
it
is
looks like a chair. So we, is it you are with
No, this is all that. I mean, okay. Now, in these systems, okay, if I have kind of these experiments are done with say particles that are uncharged. If I were to do these experiments with the particles that are charged, okay, what will happen is the moment I release these barriers, everything will go back to the 2D crystalline state. Okay, in this case, okay, when we release the barrier at at like say this junction B, it turns out some of the aggregates remain. Okay, that means the aggregates that are formed is also there some kind of interactions also play a role in this problem. Okay, so in that sense, as I said, we really cannot think about it as like a truly hard sphere system. There is definitely some interactions which we think is also because of the fact there is a interface deformation which can lead to some capillary attractions. Yeah, that's true. So, although see when people do these experiments, they try to choose as low a speed as I can. Okay, when I do compression. Okay, and typical speeds would be of the order of 0.1 millimeter per minute. That's slow enough, but still you're really not looking at an equilibrated system. Okay, it's a continuously evolving structure. Yeah.
What is the size of the system compared to this picture?
Oh,
Just a small part.
oh yeah, I mean so typically people do experiments with troughs which could be as large as half of this table. Okay, people do that, but we have done experiments with a case which is half of this the laptop. Okay, so typically about 15 centimeter by 30 centimeter of that order. Okay, so it's a collective phenomenon. It's not confined to a small region in the interface. So, as I said, in the case of spherical particles, these isotherms are reversible. If I have a highly charged particle, you do compression, okay, and then you get all these states, you release it back, it goes back to the initial state. This which dip? Yeah, I think so. Yeah, you should not. Yeah, I don't think you should because see typically these experiments take several hours, okay, at least about 2-3 hours depending upon what kind of trough area that you're looking at, and what is the typical volume of typical compression ratios you want to go to, okay. But if it takes few hours, all the alcohol would have evaporated by then. Okay, you really don't see any of these effects.
It can happen that when you again make it backwards. So some residual effects might be there. So that
So I mean, so the residual effects would actually come into picture in cases where this compression leads to some kind of aggregation of particles. Okay, because when you release the interface, only if it goes back to that initial state. Okay, when you release the barrier, only if you are able to recover that initial state, then the isotherms will be reversible. You can do multiple compressions with the same system. But the moment you have aggregates, which I am going to show would be the case if you look at ellipsoids or cases where you are working with uncharged particles, these isotherms, there is going to be some shift, okay, which would come because of the fact that or what I am trying to say is that this IP1, okay, which happened at a case with a structure like this, could be shifted to a lower area because now the aggregates would have already been present. Okay, therefore I would expect this the steep increase that you saw at IP1 to occur at a much lower area now. Okay, so things like that are possible. Okay, it depends on. Okay, I have okay, that's for the sphere. Right now we do experiments with ellipsoids. Okay, we see some qualitative differences. One is this transition going from IP1 to IP2, we think it's much more gradual. Okay, if you see that it happens over larger areas, larger area here. Okay, that's much more gradual than here. And again beyond IP3, okay, again we see much more gradual transition, gradual change in the surface pressure as a function of trough area. Okay, and we think such these changes is kind of associated with the way the particles kind of assemble at the surface. So this is a case where I have that, why do I have that? Okay, yeah, okay. So this is a image 2A, that this is the initial case where we started, right. If you look at this image, this is very different from the spherical picture that I drew. That's because of the fact that these particles, because they are non-spherical, there are these shape dependent interactions which lead to aggregation of particles. Okay, we really don't start with a gas like state. Even if you put in a few particles, they would aggregate and form form clusters. Okay, therefore I really don't have a gas like state that you saw for the case of spherical particle, and we see a lot of cases where these these side arrangement that you talked about here, Rajesh, that they form these, they line up, okay, and they form these stacks. Okay, but interestingly what you see is when I start compressing it, at some point when I look at the microscopy of the monolayer at this IP2, you see that there is all the particles that kind of lie flat at the interface, at some point they kind of flip. Okay, what I mean by flipping is if I look at this inset here, a lot of particles, they look like elliptical from the top view, but however you see a lot of spherical structures that appear in the microscopy image. These are the cases where the particles that were lying flat at the interface, they kind of flip out of the plane. Okay, and that's what is called as a flipping. Okay, and that flipping happens basically to reduce the stress that basically these particles that are there, they can't take the stress anymore that's being applied because of the compression. Just release the stress, they come off. Okay, and then if you go on compressing further, we see initially these flippers occur locally in different regions, but at some point you start seeing line of flippers. Okay, and these are kind of, the compression is being done in this direction, from here, right, and you see these line of flippers that occur in the direction perpendicular to the. Was that? See, you see here this line. Okay, this is a region where you see a lot of flip particles. So initially the particles were lying do you see here some circle like structures here? Yeah. So here again, if you look at microscopy, right? So basically, all we are trying to say is, if I look at microscopy, these interfaces, if a particle appears elliptical from the top view, okay, that's lying flat. Okay, the moment it goes over the interface, it has to look like a sphere, right? A circle. Okay, that's the okay. And this is a case where interface is kind of buckled. I mean, this dark region that you see, okay, that's because the interface is not planar anymore. there is some kind of undulations, okay, very similar to that you see for the case of spherical particle. However, we do see that when this wrinkling, when this buckling happens, a lot of particles are kind of lost to the interface. Okay, because of that, that reversibility that he was talking about is not going to be there for elliptical particles because of the fact that the moment to bring them close together, of course, you are already starting to make the particle aggregates. Number one. Number two is that because of the fact that a lot of particles are lost to the bulk, okay, these transitions are not reversible in that sense. Okay, so you would have to start experiments with a fresh monolayer all the time if you really want to see these observations. Yeah. What's that? Why do the I don't have an answer for that. I mean, so I'm just going to show you a movie. I'll just come back to this. So this is before I show the movie, this is a case where the surface pressure area isotherms were measured for different aspect ratios. Okay, and I'm going to show you a movie where you can see this. So what is interesting about this movie is that if you look at this region here, this is highly dense. Okay, at some point we see a collapse of the monolayer. If you look at it, the collapse actually occurs in the dense regions. Okay, you see a lot of space. If you look at the region here, there is a lot of empty spaces. When I am compressing, I would expect that empty spaces to kind of close, right? Or I would expect to increase I would expect an increase in the coverage there. But however, whatever the denser regions that are there, that basically take up most of the compressive stresses. Okay, and you will see that. Okay, I think the movie is still going on. So at some point, you see a jerk. Okay, and that jerk actually occurs in this region where the particles are much more jammed compared to the other regions. Okay, but in terms of the origin as to why these things occur along this line, I don't have an answer for that at this point. So I don't have an answer for that at this point. I'm not sure if it's a phase separation because it's not that it occurs at one region. It occurs all along the interface. So I don't know if you can really call it as shear banding as well, or maybe compression banding. Maybe I don't know. Okay. Yeah, fracture as well. So another interesting to notice if you look at the surface pressure area isotherm is that this aspect ratio 2.3. Okay, aspect ratio 2.3, that is these open circles here. If you look at the slope of the surface pressure area isotherm in this region, that's the steepest for the lower aspect ratio, right? That's 2.3 case. And what we have done is we have done some kind of a quantitative measurements where we have kind of pulled out a few data from image analysis. IP1, IP2, IP3, they correspond to the inflection points. This epsilon is what is called the compression modulus. Because what we do is, because I know the slope of the pi a isotherm in this region, I can use that to basically compute what is called the compression modulus. And we basically plot phi, which is the surface coverage, as a function of aspect ratio at the 3 inflection points, and then the compression modulus that is obtained from the surface the surface pressure area isotherm. You can clearly see that this epsilon kind of is kind of really high for the intermediate aspect ratios. That's because these particles kind of offer the maximum resistance for compression, and that is because these particles can pack more efficiently. If I look at the packing fraction as a function of aspect ratio, we see a kind of maxima in the packing fraction, and this maxima in the packing fraction is what basically leads to the higher compression modulus for these particles. Okay, and that's the packing density data from the 2D experiment that we just saw, and this is a maximum random packing density as a function of aspect ratio from the 3D experiments, and this is a case of for elliptical particles micron sized and the packing density measured by scattering techniques. And this is a case where the simulations have been done, and you can clearly see that there is a maximum in the packing density at intermediate aspect ratio, and that's what we kind of see in our experiments as well. Just to conclude this talk, so I hope I have been able to show you that non-spherical particle laden interfaces exhibit elastic nature. They do, there's a spelling mistake, they exhibit higher shear and compression modulus than monolayers of spheres, and that basically comes because of the fact that there's a shape induced interactions that drives their self assembly and the packing behavior. So, with that I will stop and I will be happy to take any questions.
Another question?
Yeah.
For the question before the coffee?
Some more questions, yes.
So do you think that this residual stress is going to play the role for this irreversibility? Because when you are compressing,
What kind of residual stresses are you talking about?
when you are compressing, some residual stress is present.
No, but once you release the
It may not be in the same, it may not come back in the same way like
so when I release the barriers, right, literally I have removed all the compressive stress that I applied. So, if you are talking about reversibility, right. So, I start with a monolayer, I compress it, the moment I release it, okay, no compressive stress anymore, right. It's now the barriers are completely off, now the particles are free. I mean, whatever, of course there could be interaction that lead to some aggregation and stuff like that, but otherwise there is no compressive stress anymore in the system. Okay. So, I do not think if it's going to be important.
in this again I showed cubes,
Yeah, yeah.
function of hard squares.
No, we would see the
They look like squares.
yeah.
So what kind of case do you see that the compressed mode you see column?
No, it'd be really nice to do it. See, my first PhD student, we had put him to work on this compression isotherms for different shaped objects. We could make them in the lab, but these are tricky experiments. One has to be really careful. I could do it in my PhD, but these guys somehow they think these are really hard experiments to do. Okay, we have all the tools to do it, but somehow we haven't done it. We are that's something that we.
Like in these colloids, where they do interactions to perfect the hard execution, is it possible to do that?
So you're talking about hard spheres, hard colloids at the surface.
No, like that was
It's asking hard ellipsoids. Hard ellipsoids, for example.
See,
they do something, I forget what they do. They get
no, but see the problem with these non-spherical stuff at the interface is that the capillary is always going to be there. I mean, it's very, we have kind of thought about, okay, we worked with the particles of certain charge now. Now, if I go on somehow play with the surface charge, I make it more charged now. Can I really get the 2D crystalline order that I saw with the spheres? I don't think so. We have kind of tried to do a lot of different stuff. We have never been able to do it. That means the capillary interactions are much more stronger compared to the electrostatic effects. So, unless we really come up with some magic of making particles, and we have not been able to do it. So, we have taken polycylene ellipsoids, coated them with silica and changed their wettability. We have done a few things, but somehow it does not seem to work.
So, as far as charges are concerned, I mean, if you have long-range interactions, then even at lower densities, you would be able to stabilize this kind. I mean, you would be able to see this kind of elastic movements.
I mean, in the bulk is okay. I mean, the charges are long range, but if even in spite of the fact that the charge interactions are even more long range at the interface, capillary still overweighs, for the case of shape induced stuff. So I think it's really hard to get a nice model system where I can start with a clean slate of individual particles arranged in a particular way, that gas like state, and doing compression. I think it's a little hard stuff to do it.
How do you prepare these asymmetric particles?
So, I mean, there are a lot of different ways of doing it. One of the simplest one is something like this. What you do is you take any polymeric particle, okay, PMMA, polystyrene, whatever you want to do. Take these particles, put them in a solution of some polymer, PVA, and water. Okay. Now I take this polymer solution and I put it on a plate and evaporate the liquid. I get a polymer film, okay, PVA film, and that has these particles. Now I take this film and I can heat this film to a temperature close to the Tg of the particles. Now at very close to Tg of the particle, I basically soften the particle. If I take this film and if I do a one-dimensional stretching, okay, all these spheres, they elongate and they become ellipsoids, and then you quench it and you can recover the particle back. Okay, that's one simple way of making elliptical particles of exactly same surface chemistry, but different shape. Yeah, and people have, I can take this, now I can do a 2D stretching. Okay, if I do that, I can get a disc.
Would this ellipsoids be identical? I mean, to what extent?
Oh, what I showed is that. I mean,
When you do this,
yeah. So all these
Modulus was
actually, these were actually done by that. These were actually done by that technique. The spheres versus ellipsoids. It was exactly same particles, polystyrene, and they were done. We did 1D stretching, and it's very identical. Yeah.
Now people are also using 3D printing.
Yeah, you can do 3D printing and stuff.
Okay, thank you very much.